All right, thank you for having me. I'm Alex. This talk is called Going Beyond 100% Coverage. Very briefly about me, I run a audit company that specializes in stateful fuzzing for DeFi. We are EVM only. I used to be a developer. My smart contracts handled hundreds of millions of dollars, and from that I decided that fuzzing was very helpful for security, and so I basically started Recon with my co-founder Antonio Vigiano. My experience as a researcher, I basically have about $500,000 in bounties and contest wins, and this year, thanks to stateful fuzzing, I prevented a critical exploit on Ethereum mainnet, basically saved the protocol and prevented $20 million from being stolen. Thank you. And yeah, if you want to check what we do effectively audit powered by invariant testing, and we also have a platform to run this type of test in the cloud, and soon we'll do our best to fully automate that thanks to AI so that nobody has to maintain this test anymore. So this talk is about coverage. So I'm going to take you past 100% coverage, but before we can get to that, we need to get to 100%. So obviously, there's many definitions to coverage. It could be line coverage, branch coverage, modified decision and condition coverage. But for the sake of argument, I'm going to use some new terminology that hopefully shows you the idea visually. I'm going to also show you one of our internal tools related to that. And so even though coverage is not the holy grail in the sense that you will find all bugs, it is still the best metric we have to measure our progress, and we would evaluate both formal as well as concrete tools based on their ability to test various combinations. Therefore, it's not the full picture, but it's a very good guiding function for progress. I'm going to quickly construct this idea of a coverage class. We're going to quickly see them, so if it's a bit too abstract, don't worry. I'm going to dig deeper, but fundamentally, given a function, we're going to take all the storage values that can influence it, we're going to take all the inputs, and we're going to create some sort of a mathematical group where we have the storage combinations and the union with all the possible inputs, and we then specify all the possible coverages that derive off of that. Therefore, we can have three types of coverage classes. We can have a non-reverting coverage class, which is what we would use to explore state and explore combinations. We would have a reverting class, which for the purpose of fuzzing is not particularly useful, but it could still be useful to identify denial of service attacks. And lastly, we would have an assertion breaking coverage class, meaning a set of inputs and states that will lead us to break an assertion. This is the type of targets that we want to hit for invariant testing. And if these ideas sound roughly similar, it's because I didn't know that other people already wrote about them. You can likely find them in the literature as extended EPAs, extended enabled preserving abstraction, or as the idea of modified condition and decision coverage, which is how NASA tests its own software. But the key idea is really we analyze its function, we look at the preconditions, the various states, as well as the inputs that will reach the specific coverage, and we group them together because symbolically and mathematically they belong to the same group. And so when we want to visualize them, I'm going to show this internal tool called the inliner, and basically I have a simple function here from Liquidity's governance. And you can see that we have various paths. This is very similar to how a symbolic tool will think. We basically have a case in which we have 0 votes, so we have an early return. We have a case in which we have non-zero votes, and the payout per vote is non-zero, so we will cover the entire function. And then we have a scenario in which there are non-zero votes, but we also have 0 total votes, and I think we get a revert or something like that. And obviously, this becomes insanely overwhelming. You can see a very small function from Liquidity's governance again, and this will probably drive anybody insane. But I'm not advocating for you actually doing this, but I'm advocating that as you formalize your auditing process, this is how you formalize it. This will guarantee that you have effectively went through all the combinations. And so even though this is superhuman, I wouldn't define this as impossible nor useless. So as I said, I would suggest, this is how I would say that an auditor could quantify that they're done. and yet we will still miss bugs. So the takeaway from thinking about coverage classes is that formal tools as well as fuzzers could visualize their progress through these UX stuff, and they will basically show us the progress that they're making. Obviously, the real holy grail of coverage will be path coverage, meaning you try all the combinations symbolically for all possible inputs. But fundamentally, even just having the ability to know that we explored certain of these combinations is a massive step towards in terms of improving the developer experience, as well as the ability of guiding the fuzzer, or at least getting some feedback from the formal tool, which at this point would just tell you that it timed out, giving you no particular actionable insight. You can read more about the, my notes. This is a GitHub repo I open sourced, and it will likely continue to change as I read the literature and think about this more. So this is kind of the, let's say, the more academic part of this, whereas now we're gonna go into the more pragmatic aspect. So the key question is really, why can we hit 100% coverage? Why can I give any tool, a fuzzer, formal tool, etc., the ability to explore all the states, and I can still miss bugs? This is really the key question, and as I said, even symbolically, we could explore all the combination and still miss bugs, which leads us to the fact that coverage is insensitive to the bugs, and more specifically, it's the equivalent of you going on a hike and being so focused on just making it through the hike that you miss all mushrooms, whereas somebody else that is more experienced can enjoy the view and can fundamentally pick those mushrooms. So my intuition is that obviously code is math. We can express coverage as a system of equations that we have to resolve, and therefore bugs must also be a property of the math that we're looking into. So I don't really have a exact answer. I can't point you to a formula to find a bug, but I think we can all agree that if you have a system of equations that gets you to coverage, then you have to do something to that system of equations in order to find the bug. There is a missing piece there, and over time I think we're gonna zoom in into a few types of bugs, although obviously we may never be able to find all of them. So as I said, symbolically, you have a formula, so likely there is a more complicated formula that is basically exploring less state space. And so if coverage, if whatever gets me to cover this is an elegant formula, then there's likely an uglier formula, which is likely the intersection between the formula that gets me to coverage and some other property that will lead me to a smaller state space and basically will lead me to the interesting state space and bugs, which is kind of what we do as auditors. And as such, I think there's a big parallel between this idea symbolically and then this idea pragmatically. So yeah, my key insight or my key thesis here for this talk is that for the purpose of making you think and giving you something actionable, we're going to effectively extend the definition of coverage by adding more to that metric, meaning that we're still going to use coverage, which, as I said, is blind to bugs. So it's still fundamentally a faulty approach. It's we're likely to still miss bugs. However, as we introduce more, effectively more lines, more aspects of the code as part of the way in which we evaluate coverage, that gives us a chance to miss less bugs that effectively match with this framework. So this is the key idea. Fundamentally, this is from academia. Having a high coverage doesn't strongly correlate with finding bugs. However, having a big test suite that effectively chunks the code into various components does correlate with finding more bugs, meaning that if you normalize for test size, meaning you just take the minimal set of tests that will lead you to coverage, you are actually, coverage is not particularly effective. However, in practice, just effectively throwing a bunch of stuff into your test is actually fairly effective. And so The key idea is really we're going to extend coverage by adding new lines, and I'm going to talk about exactly these lines. So this is where this becomes a bit of a esoteric talk, a bit sci-fi. Bear with me. Hopefully the journey is worth it. So the first level of new coverage or extension of coverage will be implied lines, which is the idea that some lines of solidity imply other lines that either the compiler is adding and we're not seeing, or that are executed through the node. A pretty good example would be message.value or a token that doesn't return Boolean, such as USDT. These lines of code are implied by the code that you're writing. So when you write a for loop with message.value being sent in a loop, meaning you introduce a fairly simple bug, the lines that you're supposed to be covering, the lines that you're supposed to be testing for, are in the EVM node. As such, the coverage, the way we measure it, which is just line coverage or branch coverage on the contract, is completely insensitive to that because it's not accounting for the fact that that code is covering those parts of code. And as such, if we add a way to incorporate that, we will find bugs. Another great example will be an overflow, where an overflow is effectively the operation, or it happens because we introduce a value, and then the compiler automatically inserts a mask to alter that value. As such, if we had an explicit check for every overflow that no truncation is happening or no alteration is happening, we will be able to catch all overflows at all times, whether they're useful or not, because some overflows may be done on purpose. But what I'm really saying is that the compiler, like uint88 of a uint256, is implying a truncation, and we, as the human, we are blind to it, but the code is actually there. We're just not measuring it. So I feel like this is the most realistic example of an implied line. We're going to get more esoteric as we go down the list, but hopefully this, again, makes you think about how we could measure this better. So as I said, message.value, obviously the line is only here. It's just this line, but what's really happening is account.balance minus equals, etc. in the node, and we're also getting the balance, etc. And so those lines exist. We can all agree that they exist. Is that our methodology is blind to it. So this is actually solvable by simply writing better tools. Same for ERC20. The reason why I put the ERC20 is because I want to do a quick detour on star. The idea of star is the idea that a call could be done arbitrarily to any address. And this is something that auditors will hate you for, because fundamentally a star means that I have to audit for anything. And even formal tools just over-approximate whenever that happens. But this shows you the danger of star, because a star, meaning an arbitrary call to an arbitrary address, implies that you have to cover the universe for the line. It literally means the amount of lines that I would have to add to my coverage is infinite. So it's the definition of something that can be addressed. We call it constraining behavior. And it's simply the idea that if I'm doing an audit, I want you to provide me with the list of integrations, and then I want you to hard code them, ideally, just hard code them, make the system immutable, or provide me with a system that will ensure that those are the only integration you will interact with. Because as I'm arguing, if you want to be fully certain that of the security of your system, or at least you want to get towards that, now you have to add all of the lines from that contract into your coverage. Like, that's the only way for you to measure the actual effectiveness of tests against that. And anytime you mock an integration, you're basically asserting that that system can be simplified down to that. And most of the time, that requires more work. So constraining is a key aspect, and it's a very common reason why we get bugs, an example will be the precompile bypass. There was a signature scheme that didn't account for the fact that a precompile will effectively return true. And that's an example of having a star, where now as the auditor, I have to think of every possible combination, every possible precompile, and that can be just too much. So you're much better off hard coding those options, so that way your coverage can reach that hypothetical 100%, and you can own that code as well. So now we're going to enter the esoteric zone. So this is science fiction. All the terminologies is made up by me. So if there's any reference in academia, please share, because I'm eager to learn. But fundamentally, the next level is what I would call implied state, which is something that happens, for example, in reentrancy. Reentrancy implies that a smart contract can be in a different state. There is no storage value. There is nothing that describes that state. However, that state of execution is different behaviorally and semantically from the normal state of execution, the state of execution that we tested for. And so my argument is those type of bugs can be described by implicitly adding a storage value to the contract and then considering the coverage of that contract when that storage value is altered to be a different one. So an example is fairly straightforward, is obviously we will fix this by adding the no reentrant modifier, but you can see how simply adding a Boolean flag and then asserting that anytime the withdraw function is called with a different Boolean flag, this is a different function and this is a different coverage, will ensure that at least mentally we are considering those type of combinations. Obviously, there's a million of ways to avoid this. We will go back to the idea of constraining behavior. We would rather not have to think about this, and so we would abide by check effects interactions. However, sometimes your system can't do that, and for that reason, this is the type of logic you want to apply. You want to think about these implied lines that effectively would better describe the inaction state of the system. And so if we could just magically go into bytecode and instrument it and put various Boolean flags, this is how we will go about analyzing contracts mid-execution with these new types of states. The next level is meta properties. And this is effectively properties that we use for invariant testing, whether it's formal or concrete. But the key idea is that we take the system under test, we poke at its state, which could be the actual state or the aggregation of various states. And so what tends to happen with meta properties, which is particularly interesting based on the discussion we just had, is that the meta properties is basically cutting reality or cutting the equations in a different way, and is giving you the sensitivity that we're missing when we only think about coverage. And that's because a good example will be if you have two variables, say you have a sum of two variables where one variable and the other variable can be of the same magnitude, or one variable and the other variable can be of massively different magnitudes. If you have a meta property that describes that state, now you can now see when your system goes through a state in which one variable is leading or a state in which one variable is not leading. And so a classic example here will be perhaps describing the relation between shares and assets in a vault, or other form of mathematical operations, such as, for example, the relation between a fee and the principal. And so you can see how a meta property will make it so that not only you have a line, I don't know if I have code for this, but I basically spoke about this yesterday. I did a live event where I was fuzzing an oracle, and I showed that because from coverage alone, fuzzing the oracle would lead us to finding 0 bugs and 0 issues. And then by adding stateful fuzzing and then looking at manipulating the price, that property was basically cutting reality, was creating this intersection between the formula of coverage and the formula of the price. And in that way, we were able to see a 50 million X price manipulation. And so sometimes it's literally a matter of distinguishing between the magnitude of two variables, and it can make all the difference in the world. And so this is the code. You can check again the talk I did yesterday. It's on DSS YouTube channel. And so the last one that I have for you is world splits, something that I don't fully understand. But fundamentally, because Z is a group, it's not a group, Z is a ring, and we basically deal with integers, then we have to account for the discrepancy between our the perceived behavior of math, which will be mostly linear, mostly well-behaved, and what I drawn here in in 2 seconds to basically show what we would call a stepwise alteration. And so this type of alterations are how we find most bugs. This is my favorite bug of this year. It's in my audit report for Liquidity V2, but basically that truncation right there led me to investigate the ratio between batch debt and batch shares, and it led me to find a way to borrow for free on Liquidity. And so fundamentally, all I did, though, if you think about it, besides obviously a lot of effort, was really finding that step. And so in conclusion, the takeaways are we can improve fuzzers, we should use these ideas to better show our work, and I just want to give a massive shout out to my team, Nicanor and Not, for helping me build the stuff that I showed you. Thank you for your attention.